People who are not here, I'll record. I want to make sure that you think about this in the right way, okay? That you begin to understand what the connection is between this new chapter and the previous chapters. Yes, it's about circles, okay? And that might make you suspect that, like, we just stop what we did before and start something completely new because, and I would understand why you might think that if you thought about it because circles they curve, right? I mean, they're obviously non-polygons. I'll occasionally have a student who says words like these to me, that a circle is a polygon with an infinite number of sides. Notice that I said that students will sometimes say this to me. I did not just say that myself. I don't think that's actually a coherent concept, a coherent idea. I get somewhat the sense of what you mean when you say that, but I don't think it's strictly true. But um, the real point here is this: is that I mean, circles are just, I mean, they're not polygons, right? I mean, polygons are composed of straight segments, however many of them you've got, and circles are not that. Okay, circles, to put it simply, curve. So it would be a natural sort of reaction to this new topic to say it's like, well, okay, so nothing that we've learned so far would be of help in this context because they're a fundamentally different kind of geometrical object. And I would understand that. However, that is not true because we can actually like build bridges that will allow results from previous chapters to be brought into this new topic, this topic of circles. And really, what happens today is to develop those bridges, okay, ways to bring in results from previous chapters into this new chapter. And we will begin to do that once we're done with this first section. Okay, so this section is where we build bridges. And what that means ultimately is like all the results from previous chapters about triangle congruence, about parallels, about triangle similarity, and polygon similarity generally. That all can be imported into this chapter, and some of the most important results about circles ultimately will be derived from those results that we had in previous chapters. Okay, so let me introduce to you the concept of circles, and keep in mind that these are like bridges that allow us to bring in important results from previous chapters into this new chapter. All right, so here we go. First, the definition of circle, which of course I have to give you, and I suspect you're familiar with it, but here it is. A circle is a set of points. Of course, it's a set of points because everything in this class is a set of points. A line is a set of points. A triangle is a set of points. So, of course, a circle, of course, then is a set of points. What defines it as the set of points that it is? Well, you need two givens, okay? It's the set of points in a plane, a given distance from a given point. Okay. So if you are given a point and you are given a distance, which is of course a number, a real number, then the circle is all the points that distance from that point. And as I'm sure you know, a segment that goes from the center out to a point on the circle is called the radius. And that given point that we use to construct the circle, that's of course called the center. And here's an illustration of this, the typical picture, of course. So I have now in front of you a circle with center C. A is a point on that circle, the segment from the center C to a point on the circle A. That's a radius. We will call this, by its center point, we will call a circle like this circle C, which just means circle with center C. And there's also a nice symbol for this that I use quite often, just so I don't have to write out circles. So if you ever see that particular symbol that I just circled, that is the symbol that means circle. So together, that circle symbol and then C, that says the circle with center C. Here's something that I did not discuss in my previous class, but perhaps I should have. Sometimes students are not really clear about this, and I'll mention this and never worry about it again. We said that the circle is the set of points that given distance from that given point that we call the center, right? So in this case, again, the circle center is C and A is a point on the circle. If I were to pick a point like this one, that you would say, I suppose, is interior, looks like it's on the inside, that's not a circle point, okay? Because that's not the right distance out, okay? The interior of the circle, that is what is inside of the circle, is not part of the circle. The circle contains it, but it's not itself the circle. Does anybody happen to know? I don't know if I'll ever mention this again, but I suppose I should mention it at least once. Has anybody ever encountered the name for the union of the circle and all the points interior to the circle? If you were to imagine that you like filled in the incomplete interior, does anybody know the name of that object? And it does have a name. It's called a disk. Okay, that's the circle's disk. And there will come a point in time at which strictly it would be important to distinguish the circle from its disk. That's when we finally get to area and talk about circle area. You probably at this point can guess which of these two objects has the area strictly. Is area a property of the circle or of the circle's disk? The disk, right? Because it's the disk that covers some portion of the plane, right? The circle is like a bit or a curved line. I think I will never talk about disks again. And late in the circle, in the area chapter, when I say circle area, strictly what that will mean is the associated disks area. But nobody actually ever says that. There are places in math where people just tend to be sloppy because we all know what everybody means and we just are sloppy. So here's a postulate. We'll get 3 total. Okay, and this is all the postulates. I think are very natural. In my previous class, once I made everybody understand what they meant, what they said, everybody just nodded their heads up and down that yes, these are true. So here's the circle existence postulate. It says that if you are given a point and you're given a positive real r, that is a number if you like, then a circle does exist whose center is p and whose radius has length r. This is not the definition of circle, okay? Because the definition of circle doesn't assert that circles exist, okay? We talked about this in a previous chapter. Um, I suppose one could, without too much difficulty, define the concept of unicorn. I'm not quite sure how to do that, but we all have some idea of what that is. But one can define unicorn and not thereby say that unicorns exist, right? It's not a contradiction to say, here is my definition of unicorn, and of course unicorns do not exist, right? Definitions don't assert existence. So the definition of circle didn't say that circles exist, but of course we believe that they do. And what does it take to ensure the existence of a circle? Well, here's one set of conditions. If you have a point and a number, positive number, however you came by that number, maybe you just picked it or maybe it arose in some other way, well, then a circle exists with that point as center whose radius length is that number. And what this will really mean for us, the sort of cash value of this circle existence postulate, is it allows for certain constructions. It's like the line existence postulate, which hopefully you remember. Line existence said if you have 2 points, then a line exists through them and it's unique. What that really meant for us, what that did for us, is that it allowed in diagrams for us to construct lines where we had pairs of points. That's what this postulate does as well. It really, what it does for us is it allows constructions to be introduced into diagrams. And here's a very common kind of context or common way in which that's done. If we have 2 points, that circle existence postulate that I just gave you does entail that we may construct a circle with one as center through the second. Okay, and why would that be the case? Well, just pick one to be the center. Doesn't matter which one. Pick one to be the center, and then consider the line segment AB. It exists. That's a consequence of the line existence postulate. It has a length. That's the ruler postulate. And then let's just say we choose that length to be the radius length. Okay, which means then that a circle exists with one of those two as a center point that will have to pass through the other, like maybe, for instance, this circle. So basically what I've just told you may do then is this, is if you have some diagram and you have a pair of points already present in that diagram, then one may immediately construct a circle with one of the two as center that goes through the other one. Okay, we know that that circle exists, and that's often a very useful construction. All right. Chords and arcs. A chord is a segment that goes from a point on a circle to another point on the circle. Notice that I said segment. That means that it's straight, okay? Chords are straight. They're segments of a particular variety. What makes them the segments they are is that their endpoints are on a circle. An arc is actually a piece of the circle. So arcs curve Chords do not. And our definition of diameter is that it is a chord that passes through the center of the circle. Please be careful about this, okay? In previous chapters, as early as chapter 1, I suppose, we took great care about what definitions say and what they do not say. For instance, I'm sure I noted at some point along the way that the definition of triangle does not say that the sum of its angles is 180. I didn't just say that the sum of the angles of a triangle is not 180. It is, okay? But that's not in the definition. The definition of a triangle is just three-sided polygon. That's all you need to say. And then, of course, we're able to prove that the sum of the angles is 180. Note here that we do not say in the definition of diameter that it's the longest chord in a circle. Students will often want to say that's part of the definition. It's not. That is true. It is true that no chord is longer than a diameter. However, that is provable, and we will prove it. It's a relatively straightforward application of the triangle inequality. Okay, so just here it is. This is the total definition. Chord through center, that's a diameter. So here are some pictures. Segment AB is a diameter. It goes through the circle, center is C. Segment DE is a chord that is not a diameter. And we also have arcs as well, like, for instance, the arc DE, and I'll just emphasize what the arc is. The arc is the curved portion of the circle. Now, let me make what's an obvious point. An arc is defined by its endpoints, okay? At least partly. In the same kind of way that a segment is defined by its endpoints, right? And as a matter of fact, we just use the endpoints in the name of the segment. However, you have to be careful in the case of arcs. How many arcs are there whose endpoints are D and E, for instance? There's two, right? Which is very different from segments. And this is because circles close back in on themselves. So one could indicate the two arcs in this way, I suppose. One could have the arc that goes from D to E and travels in a clockwise fashion, and then one could have the arc from D to E that travels in the counterclockwise fashion. So there are actually two arcs that terminate in D and E. So of course this means that we have to have a way to distinguish them. We want to know when we mean one and when we mean the other, because they're different, right? I mean, one, we'll talk more about this in a moment, but one is obviously, in this case, longer than the other. Here's how we do it. Okay, we make a distinction between minor arcs, major arcs, and semicircles. A minor arc is an arc that is less than half a circle. A major arc is an arc that is more than half a circle, and a semicircle is precisely a half circle. Now, how do we designate these so that we don't get confused about what we mean? Minor arcs are named by their endpoints. Okay, so like, for instance, the minor arc DE would, it appears in this case, be the less than half a circle arc that goes from D to E clockwise. Okay. And there are other minor arcs here as well. So there's the minor arc EA that goes from E to A, again, apparently from the diagram clockwise. These are all less than half a circle. There are also major arcs, for instance, DBA. What's the significance of the middle letter in the major arc DBA? What that means is this, is that as one traverses the arc path from D to A, one is required to pass through B. So that middle letter means that we must pass through it to get from one endpoint to the other. And if we must pass through B to get from D to A, then that in this case would be the major arc. And we do the same thing with semicircles as well. So one of the semicircles that's present in the diagram is the semicircle, for instance, ADB. And where is that in the diagram? Well, ADB goes from A through D and then terminates at B. So you always must go through the middle letter. So that's how we keep the difference between minor, major, and semicircles, how we keep them separated, how we're clear about which is which. All right, so let's begin to talk about measure of circles and of arcs. The first way that we'll talk about this is it's a length kind of measurement, okay? And it's called circumference. Imagine that you're at a point on the circle, and then point A in this case, and you make one complete revolution around the circle. You just follow the circle all the way around. One will have traversed a certain distance. with units, maybe centimeters or miles or whatever length units you want, but one will traverse a certain distance. The total distance around the circle, that is called circumference. Okay, and what you must understand is that this is length. Okay, and it has length units to it. Now, there will be a connection in just a moment between length of a circumference and angle measure, but we're not there yet. Okay, so this is a length. And with that, we need to bring up another postulate, or I need to give you another postulate. I call it the circle similarity postulate. And what it says is this. Let's say, I'll tell you what, I'll draw you a little picture here. So let's say we have one circle, and let's say that we have another extraordinarily poorly drawn circle. Imagine that that's a circle. And then here's what we do. Okay, so we get the circumference from the first, and we get the diameter from the first, then we get the circumference from the second, which again is the total distance around, right? And the diameter length in the second, and then we form the ratios, circumference over diameter for each. What would you suppose is true of those two ratios? Would you believe that they are equal? Of course you do. This is one of those points in the class where it's like, okay, here's the postulate. You now understand what it means. Do you believe it's true? Of course, right? This seems to me very much like similarity, doesn't it? Because what does similarity imply? In the case of polygons, it implies, part of what it implies is proportionality, which is equality of ratios. So what I've said here is that the ratios of circumference to diameter are equal. So let us call this the circle similarity postulate. Now, this links up with a certain concept, a certain name with which you are familiar. Do you know what this value, this ratio is typically called? It has a name. The ratio of circumference to diameter. You're not going to say it. You're going to say it. It's pi. Okay. So what I've really said is this. Okay. What I've really said is this. I've really said that the value of pi is the same for all circles. Okay. So here's a picture to illustrate, I suppose. So what we could do is we could compute a value for pi for our first circle. We could compute a value for pi for our second circle, call that pi sub 1 and then pi sub 2. And how do you get that? Well, take the circle circumference and divide it by its diameter and do that for each circle. So what I'm saying is that those two pi's are equal. That's the circle similarity postulate, okay? Is that the value of pi is the same for all circles. Which means then that we don't have to talk about pi for this circle or pi for that circle. We can talk about just simply pi, which is the same value for all circles, which is what we do, right? You might not have ever really explicitly thought about it, but when you use that symbol pi, and you say that it is the same for all circles, one has supposed that all circles are similar. Okay? So that's our second postulate. Now, I thought I would take a moment to derive some of the familiar equations that relate circumference and diameter and radius and pi. And what I want to make clear is that they ultimately just derive from the circle similarity postulate, okay, which again says that pi is a constant. Pi is the same value for all circles. And here's how we get that, right? So take the circumference of any circle, take its diameter, divide them, you get pi, okay? And then you can manipulate this equation in various ways. So that's like form 1, let's say. Here's another form in which you can write that equation. Multiply both sides by d. And again, this is not hard. This is really very simple. I just wanted to make sure that you understood where these equations come from. I'm sure that some math teacher in the past has thrown them at you. I just want you to understand their origin. So multiply both sides by d, so d over d is 1. So I get c is, after I rearrange a little bit, c is pi times diameter. That's just the definition of pi rewritten, okay? This is not like some deep discovery. It's just a rewrite of the definition of pi. And then, of course, one can write this in a third way. What's the relationship between the diameter length and the radius length? It has to be 2r, right? And that's not like some deep result either. I mean, it's just, what is the diameter? It's a chord through the center, which means that it is 2 radii, right? that follows immediately. So D is 2R, which means that one can now substitute. So C is pi times 2R, which typically gets, oops, wrote that wrong, sorry. So pi is 2R, which typically gets rewritten, right, as 2 pi r. So again, not a deep discovery. All of these are just ways to express the definition of pi, together with that assumption, of course, that the value of pi is the same for all circles. That's all those ever were. Okay. Now, let us really build at this point. I talked a moment ago about like bridges between previous chapters before this one and this chapter that allow us to bring in results from previous chapters into this chapter. This is the most important one right here. Okay. A central angle. What is a central angle? It is an angle whose vertex lies at the center of a circle. Okay. So I've illustrated this. Let us say that we have circle with center C, and then we have constructed, obviously these are radii, then CB and CA. Together they form the angle BCA, which we say is a central angle because its vertex is the center of the circle. And there it is. I mean, there's an object with which we're well familiar, an angle. Oh, and just to look ahead a little bit, what, of course, do you know about BC and BA? Excuse me, not BC and BA, but BC and CA? Of course they are, because they're radii. And then what if one were to do that? As one might. You see what you now have? You have an isosceles triangle. It's like, oh my goodness, maybe the isosceles triangle theorem will be important in this chapter. The isosceles triangle theorem will be absolutely foundational in this chapter. What is probably the most important and powerful result of the entire chapter, which is called the inscribed angle theorem, which we prove about halfway through, ultimately its foundation is, one of its twin foundations is the isosceles triangle theorem. Okay? As a matter of fact, the connection between them is so close that I tend to think of the inscribed angle theorem as like just the isosceles triangle theorem for circles. You'll see, okay? So perhaps you begin to get a sense of how it is that we can use prior results in this new chapter. We need one final postulate, and it's called the central angle postulate. And I think you'll find it plausible as well once you understand what it says, and I think it's a little bit harder to understand. Okay, so assume that we have a central angle. I'll show you a picture in a moment. I left one thing out. One bit of terminology here that will be important. You would have picked up on it, but I'll make sure you understand. If you have a central angle, then of course a portion of the circle lies inside of that central angle, which is an arc then, of course. So in this case, arc AB lies within central angle BCA. We say that this is the arc that is cut by the central angle. The old language for this, if you like pick up an old geometry textbook, like from the 19th century or earlier, I have a collection of them. The word is subtends. They would have said that angle BCA subtends arc AB. I like the language of cuts better than that, which is also more common today. So angle BCA cuts arc AB. Now here it is, the central angle postulate. So let's say that we have a central angle that cuts a portion of the circle circumference. We postulate that the angle's measure is to 360 as the length of the arc cut is to total circumference. Those two fractions are the same. Let me show you what I mean. Okay. So again, here's the central angle. Let's say that the central angle has measure alpha. Let's say that the length of the arc, that's a length measure, some number of centimeters or something. Let's say that that is L. And let us say that, I've already used C, but I'll use it again. I think this will be clear. So let C represent circumference. Okay, so what I'm saying is this, is I'm saying that the measure of the central angle is to 360 as the length of the arc is to total circumference. That's what this postulate says. Do you believe it? Is the fraction the same? That is, if, say, BCA was 90 degrees, would that mean that the arc is 1/4 of the total circle? I mean, 90 over 360 is 1/4, right? Would the arc have to be 1/4 of the total circle? Do you believe that?
Yeah.
Of course you do. Now that you understand what it says, of course you believe that this is true. Okay, so that's the third and final of our postulates. Now, there's something that everybody always does, and this used to trouble me a little bit. I think it troubles me now that less than it used to. There's actually a deep mathematical story behind all of this. I'll give you just like the first version of that story. There's a courtesy. I think that's the best way to talk about it. A courtesy that we pay to arcs. We know that they have length, okay? Of course they do, right? As you go around a circle, you traverse a certain length, whatever that is. But we will also talk about them as if they have a degree measure as well. That is, we will talk as if arcs have both kinds of measures. Well, how then does an arc get its degree measure? Here's what we will say. And I think this is best treated as a definition. We will say that the degree measure of an arc is the same as the degree measure of the central angle that cuts that arc. And I guess it would be good to have a picture here, so let me draw you a quick picture. Probably should have had one ready to go. But let's say that we have a central angle that measures something like, I don't know, 30 degrees. Then we will also say that the arc that is cut by that central angle also has a measure of 30 degrees. It, as it were, transfers. Okay, so from central angle to arc. That means that we have two sorts of measures of arcs. We have the length measure, which is, of course, a fraction of total circumference. And then we also have the degree measure, which is a fraction of 360. The same fraction of 360 as the central angle that cuts that arc. And we will absolutely continue to talk about arcs in both ways. We will give measures of both kinds. Mostly, we will talk about the degree measures of arcs. Okay, occasionally we will talk about their length, and I promise you that the language that I use will always make this clear, which I mean. Okay, if I mean the length of an arc, I will say arc length. If I mean the degree measure of an arc, I will say measure. Okay, I'll be consistent about that. But mostly we'll talk about measure. But just remember what that means. Okay, talk of the degree measure of an arc is just really talk of degree measure of the central angle that cuts that arc. Okay, and with that, we're done. So that's the first